welcome to Intro to Functional Programming in Haskell. Today we're going to be talking about recursion and lists. Repetitive processes and nested operations are expressed with recursion in Haskell. As a matter of fact, within the language there is no for or while loop type construct. Many are dismayed when they first learn this. However, one can find comfort in the fact that it is provable that anything that can be accomplished via direct iteration can be accomplished via recursion, and vice versa. As a matter of fact, simple iteration itself can be expressed via recursion using a function such as the one shown below. A recursive function that takes a function to execute as an argument as well as an argument in, and executes that argument function n times by recursing down with a decreasing n. Something else we should take note of at this point is the concept of bottom. The language itself can detect a variety of computational errors at runtime and compile time. Failed computations end in bottom. For example, if the language recognizes that a recursive operation will never terminate, which it can in a variety of situations, that execution will stop with an error or an exception, and this exception is a way of expressing that an operation resulted in bottom. On a related note, we often find ourselves working with lists in Haskell. The default list in Haskell is actually defined recursively. It is a singly linked structure. A single list node actually is either an empty list or a single list value along with the rest of the list. If we look at the definition here, data list of A can either be the empty list or an A value or along with the rest of the list. We can access a single index of the list using the double bang operator, and lists can be concatenated using the double plus addition operator. However, lists within Haskell have to be of a uniform type, so unlike in a language such as Python, you cannot concatenate lists that have items of different types in Haskell. The double period operator indicates creating a range from two values. Lists can be built using this operator. A list from 1 to 10 will result in, as shown here, the numbers 1 through 10. As a matter of fact, if you recall back to when we first discussed enum, this double dot operator simply calls enum from to with the left argument and the right argument. So it is simply syntactic sugar for that. Another common list operation is take. Take simply grabs the first n values of a list and returns that sublist as its own list. So take 3 on the list from 1 to 10 will simply return a list containing the numbers 1, 2, 3. Another useful operation that can be carried out on lists is filtering. Filtering takes a function and a list as arguments. The function should be able to evaluate a single member of the list and return true or false. Filter returns a list that contains only the values that the argument function returns true for. So the built-in function even only returns true if the number passed in as an argument is even. So if we filter even on the number list from 1 to 10, we will receive back a list that simply contains 2, 4, 6, 8, 10. The other common way of combining lists, other than simple concatenation, is zipping. Zipping takes two lists and pairs up their items into tuples and returns a list of those tuples. So in this example here we have 1, 2, 3, 4, and 5, 6, 7, 8, and we zip it together and we receive a list of tuples of 1, 5, 2, 6, 3, 7, and 4, 8. There is a provided unzip operation that is the inverse of this. It takes a list of items that can be iterated over and breaks that list of items into two separate lists. Folding, like filtering, is a sort of meta operation. It takes a function that will operate over the members of the list as an argument. This supplied function to the fold should be a binary operation, meaning it combines two arguments. Importantly, notice the word combine. This function should be built to take two members of the supplied list and meaningfully combine them in an intelligent fashion. The other argument to a fold is the initial accumulator value. So, since a fold uses the supplied operation to combine values, how does it begin? It begins by combining the accumulator value with the first member of the list, takes that result, and then combines that result with the next member of the list until no members of the list remain. The fold then returns this final accumulated value. So what about operator associativity? Well, there are actually two different fold operations that are defined by default that you can use to apply the supplied operation in a left associative or a right associative manner. Fold L applies the operation as if it were left associative on the list. Fold R applies the operation as if it were right associative. In the example below, you can see, as expected, using fold R with the addition operation as the folding operator, and starting with 0 as the accumulator, over the list 1 through 3 returns 6, whether we fold left or fold right. This is expected. If an operation is not associative, like addition, then we would get different values for the right fold and the left fold.